Hello everyone. We are going to be talking today on column space of a matrix. Let's define the column space of a matrix. The column space of a matrix A of size m by n, written as col A, it is the set of all linear combinations of the columns of A. So if your A has n columns, suppose A1, suppose this is the matrix, A1, A2 up to AN. Remember, each of the AIs is having m rows. Okay, so your column space of A is nothing but the set of all possible linear combinations of the columns of A, which is basically the spanning set of all possible linear combinations of A. Now, if you recall the matrix equation, what is B? B is all possible linear combinations of the matrix A, isn't it? Such that this matrix equation is consistent. So we can also say that column space of A is collection of all B's where AX equal to B for some X in Rn, and A is a matrix of size m by n. So we're talking of a very general matrix. So let's look at some observations about the column space of A. If A has a size m by n, I'm talking of a very general matrix, column space of A is a subspace of Rm. Remember, what is the column space of A? It is the span of all the columns of A. And how many columns it has? N columns. A1 up to An. Now notice, where is A1? A1 has m rows. Okay, so A1 has what? M rows. So clearly column space of A is the subspace of Rm. By the virtue of the definition, it is the spanning set. And we know from theorem 1 in our vector spaces, that is section 4.1, we talked about that the span of a set of vectors from a vector space is always a subspace. So clearly, by the virtue of the definition, column space of A is a subspace of Rm. It's explicitly defined. Why? Because you can see what is column space of A is made of. It is explicitly defined in terms of the columns of the matrix. Now, a very important property is a typical vector in column space of A will have the property that AX equal to V is consistent. This comes from the definition. We say it is a collection of all those B's such that AX equal to B for an X in Rn. So that means, and it's like all possible linear combinations. You're looking where X is an element of Rn. And A, remember, is an m cross n matrix. So basically you're saying is it's a collection of all those B's such that this matrix equation is consistent. Now, this column space is the whole of Rm if and only if the matrix equation has a solution for every B in Rm. So these observations are very, very important. Now let's go ahead and do some examples. Now, we are given a matrix equation where A is given by this matrix, and we would like to know, is the element 1, -9, and -3 an element of column space of A? Remember, very important, column space of A is a subspace of Rm. So we have to know what is Rm here. So this A is what? It's a 3 by 3. 3 is the number of rows and 3 is the number of columns. So we'd like to know whether it's an element. Before we can even say it's an element, it has to be an element of R3. So this, suppose this is, say, X. Clearly X is an element of R3. Notice how I'm color coding it. This 3 means the number of rows. Yes, so first of all, yes, it is. Column space of A is in the perfect sense, because remember we are saying column space of A is a subspace of R3. That is by default. So now, even if you're picking up an element, it has to be first of all an appropriate element of the appropriate space. So clearly, X is an element of R3, so we're good to go. Now, whether it is an element of column space of A is basically saying whether this matrix equation is consistent. And if you remember the algorithm you are trying to apply it on, in other words, you want to say is that the augment matrix, which is given by -1, 3, 2, 1, 2, -3, 2, 1, -2, 1, -9, and -3 is going to be workable. In other words, if I can write this, applying all those row operations and reduce it to a row reduction, REF, such that we get an identity matrix. And the reason I'm writing it into an identity matrix is because I need to know what are these elements of X. So we apply the row reduction algorithm and we find that, yes, we are able to get the values for X such that when you multiply the columns, 2 with the first, second with the -1, and third column with 3, you will actually get this matrix. So the standby guys, I know you know how to do it. You can apply the algorithm and you don't have to go till the echelon form. Echelon form says yes, it is going to work, because we also want to know what are those elements of X. So it's important is we need these elements of X. And once we get it, we will notice, so let's see that when I multiply 2 with -1, 1, and 2, -1 times 3, 2, 1, and +3 times 2 -3 -2. Okay? Now remember, if this is an element of column space of A, that means this can be written as linear combinations of these 3 columns of A. And that we can do is by applying the row reduction algorithm, those elementary operations. And if we can write this matrix A as an identity matrix and we get some values on the very last column, so automatically we know what are the values by which it is going to be equal to this. So let's check it also. This is equal to 2 times -1, -2, -3. Okay, so -2 -3 is -5 plus 6. What do we get? 6 minus 5, a 1. Then 2 minus 2, a 0. And 3 times -3, a -9. Great, we are already getting the first 2 elements. Let's look at the last one. 4 minus 1 is a 3. And 3 minus 6 is going to give us a -3. So yes, this element can be written as a linear combination, and we also know what are those values which makes this X an element of the column space of A. So just remember, if you want to prove that something is an element of the column space of A, the first thing is check whether that element is in the appropriate R-dimensional space. And that can only be if you look at what is the column space a subspace of. Second, you apply the row elementary operations and reduce it to an echelon form. Once you get the echelon form, you have an idea whether the system is going to work or not. And after that, you have to go and write down the identity, go ahead and further apply the row reduction algorithm and get an identity matrix so that the last column gives you the values of the variable by which when you multiply to the columns of the matrix, you actually will see the element you are checking on. So those 2 steps to keep in mind. Let's go ahead and look at another example. Now for Ax equal to B, where this is my A, The question is this element 2, 3, 1, 0 an element of the column space of A? Now guys, remember once again, you have to look at whether this is an appropriate element before we even apply the algorithm. So this is a 3 by 3 matrix. And we know that the column space of A is a subspace of R3. So clearly, these two numbers match. So any element of the column space should be an element of R3. Let's look at the element which is given to us. This vector is an element of R4. So if you look at this one, suppose this is Y. Now Y is an element of R4. R4 is not the same as R3. So we don't even have to go further because this element is not even an element of R3. Therefore, Y is not an element of the column space of A. Okay, now we're going to do some examples from the book in this column space of the matrices. Okay, so it says let W be the set of all vectors of the form C minus 6D, D and C, where C and D are real numbers. So the question is whether this W is a vector space or not. Now, remember one thing. In our previous videos, when I talked about vector spaces and subspaces, we said that if I could write a set as a linear combination of some vectors, and that means I'm talking of a spanning set, and every spanning set is a subspace, and every subspace is a vector space. So keep that thing in mind. So if I want to see if this W is a vector space, what I literally have to see is this W can be written in the form of a spanning set of some vectors. Okay, so let's look at this C minus 6D. So W has all elements of the form C minus 6D, C and D. Okay, let's write it down. So I can write this as C0 plus minus 6D, 0D, which I can take the C out, I get 1, 1, 0, plus a D out, minus 6, 0, 1. So clearly W can be written as all possible linear combinations of the vectors 1, 1, 0, minus 6, 0, 1. So W is nothing but the span of two vectors, 1, 1, 0, and minus 6, 0, 1. And we all have learned previously that the spanning set of vectors is always a subspace. So clearly W is a subspace of, what are the vectors in? R3. Okay. Now if you remember, this is theorem 1 in section 4.1 of the book. Now, we also know that every subspace is a vector space. Therefore, W is a vector space. Okay? Now, let's look at another example. It says if W is the set of all vectors of the form B minus 5D, 2B, D plus 1 and D, where B and D are real numbers, find if W is a vector space or not. Okay, so let's go ahead, write this W as B minus 5D. See if I can, remove B's and D's, and if I can get right as a linear combination of subsets. So I can write this as B 2B 0 0 plus minus 5D 0 D D, and then I have this constant 0 0 1 0. Now clearly notice what happens. If B is what? 1 2 0 0 plus D is minus 5 0 1 1 plus 0 0 1 0. Notice, if this has to be a vector space, that means it will take all possible linear combinations of this. So if I give my B and D, if my B is 0 and my D is 0, what happens? This W will be written as what? It will be 0 plus 0, and in the end I would have 0 0 0 plus again a 0 0 0 0 plus 0 0 1 0. That means I will never have a zero vector. So as I am not going to have a zero vector, then I will not have a vector space. So what is the answer? W is not a vector space as it has no zero vector. Do you see that? Zero vector is a must for any set to be become a vector space. Okay. Let's look at another example from the book. We're given W to be the set of the vectors of the form A, B, C, D, and the relationship we see is that A plus 3B is C, B plus C plus A is D, where A, B, C, D are real numbers. So we'd like to know whether W is a vector space or not. Remember at the back of the mind? If it is a vector space, that means can I write it as a spanning set of some vectors? Okay, let's look at what we have. We are given A plus 3B to be C. Oh, C can be written in terms of A and 3 B's. Okay. Then I can write D as B plus C plus A is D. In place of C, I can, write A plus 3B. What do I get? B plus A plus 3B plus A is D, or B plus 2A plus 4B plus 2A is D. Okay. So one is C can be written in terms of A and 3B, and D can be written in terms of B and A. So let's look at my W. How can my W be written? W can be written as A, B, C, D, which can be written as A, B, A plus 3B, and 4B plus 2A. That means I can write my W as 1, 0, 1, 2 plus B times 0, 1, 3, 4. So clearly W is the span of these two vectors, and hence it's a subspace and it is a vector space. So W is nothing but the span of the vectors 1, 0, 1, 2 and 0, 1, 3, 4. Therefore, W is a subspace of R4 by Theorem 1, Section 4.1, and hence W is a vector space. Okay? Now, let's look at another example. It's coming in a different form. It says find a matrix A such that W can be written as a column space of A. What it basically means that if I can write W as the spanning set of some vectors, those vectors can become the matrix. So let's look at this one. Oh, sorry, this is not needed, guys. So W is what? It's B minus C 2C 3B. I can write this as B 1 0 3 plus C minus 1 2 0. So clearly, notice W is the span of the two vectors 1 0 3 and minus 1 2 0. And what do you say? W is in the column space of A. What does that mean? All possible linear combinations of A. So make your life easy. You say B is 1 and C is 1. So basically it is sorry, not B and C is 1, sorry. W, we want to write a matrix so that it is a column space of A. Okay. In other words, you want to look at the vectors, which if you take all possible linear combinations, that basically makes up the column space. So make your life simple, guys. Just write A as what? Just pick up these two, because that what is nothing but the columns of the matrix A. 1 0 3 minus 1 2 0. So what do we notice? If I look at all possible linear combinations of A, I'm basically talking about the spanning set. I'm basically talking of the column space of A. That's it. Okay, now I'm going to talk about some linear transformations. So before I talk about the specific kinds of kernels and ranges of a linear transformation, let's recall the definition of a linear transformation. A linear transformation from a vector space into a vector space is a rule which assigns to each vector in V a unique vector T of x in W such that T preserves vector addition. In other words, when T acts on U of a sum of these two vectors in V, it is basically as you're individually acting, the T acts on U and on V separately, and then you add them up. And then T, when acts on a linear combination of any vector U, it is the same as that T acts on the vector U and then you multiply it by a C. So when I say T is a vector space into a vector space, in very simple words, T is a linear transformation from V to W. Okay? Now let's talk about the kernel and the ranges of these linear transformations. Now, the kernel of a linear transformation is the set of all those u's in V such that T of U is 0. Remember, T is a linear transformation. That means T is a linear transformation, or if you forget, it's a function, if you're mapping or whatever you want to call. T is a mapping from V to W, okay, where V is the domain of the linear transformation and W is the codomain of the linear transformation. Now, kernel of T means all those elements V in the capital V such that T of V is 0, or U we want to say. So it's basically it is the set. So kernel, the way we say is kernel of T, collection of all those U's in V such that T of U goes to the 0 vector in W. T of U is an element of W, remember that. So basically it is just like a null space, isn't it? Null space was what? It is set of all those vectors in the R, and depending upon what matrix we are looking at, such that the matrix times that vector equals 0. So kernel of T is the same as a null space of the appropriate or the standard matrix corresponding to T. Remember, we've talked about that every linear transformation has a standard matrix. So the null space of that standard matrix of a linear transformation is nothing but is equivalent to the kernel of T. Okay, so the range of T. What is the range of T? It is a set of all those vectors in W of the form Tx for some x in V. So if I make a little, mapping here. So this is my V and W, some spaces. And T is a linear transformation from T to, takes elements from V to a unique element in W. Okay, so what does this range of T means? Now, this is the codomain, remember? So if all those elements, when acted upon, goes to this little blue thing, so this is called the range of T. In other words, every element here has an element related to the whole of the space. That's what it means. Okay, so the kernel of T is a subspace of V, because where are the elements of kernel coming from? They're coming from the domain of the linear transformation. And the range of T is all those elements in the W which has a preimage in V. So the range of T is a subspace of W. And that's what we need to know. And on that, what we're going to work on the problems. Okay, so let's look at an example here. Given a matrix, find K such that the null space of A is a subspace of what Rk. Now, the first thing you need to do is, whenever you're given a matrix, guys, write down the size. The size of this matrix is 3 by 4. Now, remember, the null space of A is, just to remember, null space is all those x's where x is an element of Rn for a, such that Ax is 0 and A is an m by n matrix. So the moment you keep this in mind, that means your K is being in sync with the number of columns of the matrix. So here my K is 4. On the other hand, what is column space of A? Column space of A, we said, is a subspace of, if I go back here, is a subspace of R to the power m. So that means, you know that from the observations we talked earlier. So column space of A. So what is my K here? So my K is 3. Okay. So these were some of the problems. And now I would like you to work on these problems from the book. So 1 to 5 are basically related to null space of A. So all the problems which we have done so far, they are going to be in the ranges from 7 to 26. All these different problems I've given. Practice them. Very important for you guys. Thank you.